Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Good afternoon. It's my great pleasure to introduce Chris German, who is visiting us from University of Florida, Gainesville. He did his PhD at Georgia Tech, finished it in 2002, and then joined the faculty. He has been very successful in publishing, all of you know, including this year's SIGMOD, co-recipient of this year's SIGMOD Best Paper Award. He's also a winner of the NSF Career Award. And his general area of interest is databases, engine, as well as the data analysis techniques. And today he's going to talk about the online statistical processing.
Okay, thanks a lot. And actually, so I see that several of you were actually at my talk at SIGMOD. And so unfortunately, I've got to admit that for the first half of this presentation, it's going to be a rehash of that. So you can just take off and come back in a half hour. Otherwise, or check your email. Okay, so this stuff, if you did see that, it'll look pretty familiar. But anyway, so in general, I'm going to be talking today about database performance. Okay, so this is the motivation for the kind of work that we do. And so I can tell you from giving similar talks at different places, people often ask, well, you know, there are so many other issues, pressing issues. Should we be worrying about database performance? And so I'd argue that actually, yes, it's still an important problem. Okay? So this is from actually several months ago now, but if you take a look at the most recent Pch benchmark results, and by the way, in case you're not familiar with the database area, Pch is a benchmark that and companies, it's essentially an industry consortium of hardware and software vendors, and there's a benchmark, a set of SQL queries that they try to optimize for and report their running times. And so if you take a look at these recent results, it turns out that you can actually spend almost $1 million to store only 300 gigabytes of data. And it's actually interesting that this is done in this particular result with 17 terabytes of 36 gigabyte disks. And in this case, query 21 still takes 18 minutes to answer in the throughput test. So this is one of the queries in the Pch benchmark. So this is actually quite extraordinary, okay? That you're storing a database for almost $1 million on something that you can actually put on a single disk, and the query still takes on the order of tens of minutes to answer. And it gets a lot worse if you've got a bigger database. So if you've got 10 terabytes, well, the best results show that you can still spend on the order of $10 million, and then you're waiting 4 hours for query 18 in the benchmark to finish. Okay? So this is not good performance. And the conclusion, kind of motivating our work, is that if you're trying to do analytic processing, which is what this benchmark is, so you're doing data analysis, the analytic processing solutions we have just aren't that great. And the result is that it's difficult to treat the database management system as a sandbox, where somebody just has a database and they kind of see what's in their data. That's really not feasible now. Okay, so our solution to this, the solution we're very interested in, is to use approximation. And this is motivated by 3 key observations. Okay, so the first one is that when you're doing this kind of analytic processing, the queries that you're asking are almost always statistical. So they tend to have kind of grouping and so on, but in the end, you're usually looking at aggregates, counts, sums, mins, and maxes. And in the case that you're answering statistical queries, it's not clear that something like 1.3745 million is always different from 1.3757 million. Now, it might be different, but it depends upon exactly what's being asked and what you're doing. And if there is not a big difference between these two things, why waste a lot of time and effort to get down to the 4th decimal point? And then another observation is that quite often most exploratory queries are wrong, where if someone's really just playing with the data, they ask a question and they find out that what they were asking is actually not interesting. They asked the wrong question. And so this actually kind of goes back to the second point, because if you ask the wrong query, then a few decimal places might be enough to tell you that you're kind of going in the wrong direction. So given all this, imagine that we had the following database management system, okay, where you could, number one, you'd ask any analytic processing style query, and you'd get an immediate guess as to the final answer of the query. Number two, this guess would be bracketed by meaningful statistical error guarantees. Number 3, this confidence region, or this error brackets, they shrink throughout the online computation. Number 4, these brackets are zero width at completion. So as you wait, you get closer and closer to the answer, and eventually you're 100% accurate. And then finally, the time to get to 100% accuracy should be no longer than it takes to get to 100% accuracy with SQL Server or Oracle, or pick your favorite database system. Okay? So the total execution time is the same as in a classic RDBMS. Okay, and so many of you who are familiar with the database area, you might be asking, well, hasn't this been done before? So there was pretty well-known work that came out of UC Berkeley starting about 10 years ago now called the Control Project. And this was spearheaded by Joe Hellerstein and then also Peter Haas at IBM. And they developed these things called online aggregation and ripple joins. And they got to a couple of the bullets from my last slide. Okay, so they do online computation with error guarantees. But they didn't consider the problem of scalability, getting to the end of the query. And they also didn't cover the issue of generality. Okay, so they could handle kind of very specific select project join queries. And I want to really stress the scalability issue, at least in the first part of my talk, because, well, as I'm going to talk about in detail in a minute, online aggregation is great, but as soon as you process enough data that you can't store all the tuples you've seen in memory, then all of the stuff that Peter and Joe did in the UC Berkeley Control Project can't be used anymore. You're done at that point. Okay? And I'll stress this point in a second. Okay. So, our work. Well, like I said, this online aggregation stuff, in the end, it was really more of a very successful attempt, I think, to add functionality to an RDBMS. They didn't talk about how you can change things fundamentally to really make this processing scalable. So we feel this can only get you so far. And so our goal in this work is to redesign the database system from the ground up so that the algorithm's query processing is essentially fundamentally based upon randomization techniques. And the resulting system that we're working on designing and implementing is something called DB Online, or DBO for short. Okay, so at the outset, this whole thing of giving guesses to the final answer to a query seems pretty hard to do. So let's say that you got a query plan like this one. So we've got a four table query with a set-based subtraction in there, and we're trying to guess what the final answer to this query is. So how in the world would you start out and be able to give a nice answer from the start to the finish of this query? What in the heck are you going to do to make this work? Well, in this UC Berkeley Control Project, in a very well-known paper Haas and Hellerstein wrote in 1999, they gave us something called the ripple join, which is actually very useful for working on this kind of bottom part of the query plan. So this ripple join thing that Haas and Hellerstein came up with, it's great for this. It doesn't work for the entire query plan, but it's at least a very good starting point. And so I'm going to spend a few minutes going over it because it was really fundamentally what a lot of our work is based off of. Okay? And by the way, if you got any questions or comments, please stop me. Okay, so the ripple join. So let's say that you got these two tables, and you're trying to guess the answer to an aggregate over the join of the two tables. So what does the ripple join do? Well, the idea in the ripple join is to take the two input relations, and you take these things and you permute them randomly on disk. So you start out by shuffling these things randomly. And by the way, this is done offline before you ever start computation. So the data is actually living on the disk in a randomized order. So we start out doing this. And then what you do is you start your table scan operators on the base relations. So at this point, what I've done is I've got this black square here, which means that the table scan has scanned one tuple from sales, it's gotten Tom, and it's got a second tuple from emp, Jan. Okay? And what's going to happen, what the ripple join does is it takes the query, which is a very simple sum over an equijoin here, and it executes the query on the subset of the database that happens to be in memory, in this case one tuple from each input relation, and it gets a 0, okay, because the sum is now 0. So that's where the 0 comes in. Then you take that current sum over the subset of the database in memory, and you scale it up by the inverse of the sampling fraction for each input relation. In this case, the inverse of the sampling fraction is 36, because you have 1/36 of each input relation. Okay? So at this point, we get a guess of 0. Now this guess of 0 is of course pretty inaccurate because this estimator has high variance because the samples are pretty small. But as you read more data in, you start to get matches, and your guess can, if you're lucky, your guess can get pretty good pretty quickly. So in this case, we now read in a couple more records from both of the input relations. We got Jan and Tim. So you take and you join up, and you find that we now got this gray cell where Jan is joining with Jan. And so our current estimate is the 3 from Jan, and then times the inverse of the sampling fraction. So it's just 1/3 times 1/3 inverted times the 3, which gives you 27. Okay? So we're now doing much better. And the thing just keeps on going, right? So you read in more and more data. We read in 2 new tuples from each input relation. We find a match for Tom. And so we put the 12 in here, scaled up by the inverse of the sampling fraction. And you keep going. The guess gets better and better until at the very end, your guess is actually 100% accurate. And so this is a really nice algorithm. Okay? It's got some very nice statistical properties. The guess is always unbiased, which means it's correct on expectation. It's consistent, which means that as you get more data, the variance continuously decreases. And the variance, if your sampling fraction is reasonably high, can be very, very low. So it's a very nice algorithm. OK, so what's the problem with this? Well, the issue is that this whole ripple join is very high level, and it needs an actual implementation. And in practice, the only really practical implementation is a hashed ripple join. Or what you do is, as you're scanning in the 2 input relations, you take all the tuples you've seen and you store them in twin hash tables, 1 for each of the 2 input relations. Okay? So what you do is, so I got all my emp tuples I've seen in one hash table, all my sales tuples I've seen in the other hash table. When I get a new emp tuple, I first do a lookup in the sales hash table to see if it's got a match there. Okay? I update my statistics accordingly, and then I hash it to its own table, store the hash table, and then take another tuple from the other side, right? So you keep on doing this. Now the problem is, as soon as the hash tables get too large to fit in memory, you're in trouble. The whole process comes to a halt. It requires that all of the tuples in emp prime and sales prime, which are my samples, be stored in memory. And in a real life system, right, if I've got a RAID and I'm reading tuples off the disk at a high rate of speed, even if you got a lot of gigs of RAM that are sitting around ready to go here, you're going to be in trouble pretty quickly. Okay? So as a result, the ripple join is great, but practically speaking, it works only for a few seconds. And so the issue is that this might not be directly applicable, but the idea of always adding more data and always kind of looking for result tuples that you happen to find, this is central to query processing in the DBO system. Okay, so basic query processing in the system that we're working on implementing. And actually, by the way, all of this stuff that I'm talking about now has been implemented and prototyped. Well, at least not this part of the talk has been. So imagine that you got a complex query plan. So you got like this 8-way join here, okay? And I decide that here's the query plan, the way I'm going to evaluate this thing. So what is DBO going to do? Well, the first thing that it does is that all of these bottom level joins are kind of fired up at the same time. And they're going to be processed concurrently in a very, very tightly coupled fashion. And this kind of concurrent processing for all these guys is going to be something that we're going to call a level-wise step. So you start all of these joins, and they're not done independently. Like I said, they're always talking to each other. This level-wise step fires up. So they all start going at the same time. So what happens is that as all of these 4 joins are being processed, the joins are always kind of chattering back and forth among each other. And they're always kind of asking, do I happen to have any tuples in memory that could survive the entire query plan? Okay? So you got join 1, join 2, join 3, and join 4. At all times, they have some tuples in memory, right? They're going to be composed essentially of sort joins. So everyone's got tuples in memory. So the way that this level-wise step works is that they're kind of always talking about what tuples they've got in memory. And when they happen to have tuples that can combine together and will make it up through the top of the query plan, they find out about it. And they use this kind of happened to produce an estimate for the final answer to the query. And I'm going to give a more concrete example of this in a few slides. But they're always talking back and forth, trying to find result tuples. So finding or not finding these lucky tuples allows an online guess to the query result. And so this is this N1. Okay? It's a guess associated with the first level-wise step. That's where the 1 comes from. Okay. Oh, yeah.
So video, or is this just an example?
Great question. So I'm going to actually cover that in about 10, 15 minutes. Okay. So for simplicity, assume they're always bushy. Okay. Okay. So the current value of this guess corresponds to a trial over a random variable, which we'll call n1. Okay. So a nice principled way to talk about how accurate you are and come up with bounds is to say, okay, my guess for the final answer is going to be a random variable, and so I'll derive statistical properties of it, such as the bias and the variance. Well, it turns out this is unbiased, so it has no bias. Okay? But you can use the estimate of the variance along with the central limit theorem to give confidence bounds. Okay? So you can actually, it turns out that there are proofs that this sort of thing is actually normally distributed. So since it's unbiased, that means that the error is a nice normal bell-shaped curve around the correct query result. And so if you know the variance, you've got nice confidence bounds. Okay? So eventually, this first level-wise step completes. And all of these lowest joins are now done, and you've got A, B, C, D, E, F, and G, H. These 4 result relations are sitting there. Now, of course, in practice, they're probably going to be pipelined to the next step, but just pretend they're kind of sitting there right now. At this point, N1 has seen all the tuples it's going to see. It's still an unbiased guess for the query result, but it's now frozen. Okay? And by the way, we've always been given N1 to the user. So as this bottom level-wise step goes, we've been guessing the result and telling the user what the guess is. So at this point, level-wise step 2 begins. Okay? So this level-wise step has its own estimator called N2, because it's a second estimator. And it's not good initially, because just like N1, it starts out having seen no result tuples. But pretty soon, it starts discovering result tuples. And it's soon going to become far more accurate than N1. And the reason is that assuming N2 and N1 use the same amount of memory, there's a lot more density in N2, right? Because you're relying less upon the randomness because you've actually condensed A and B down to a single relation AB, right? So you're relying less on the randomness. And you can show mathematically that the variance of N2 is going to be much lower than the variance of N1. Okay. So you want to use both estimates, so you don't want to just throw out N1, especially because initially N2 is not very good. So we're going to let N, which is going to be our real guess that we give to the user, it's simply going to be a weighted sum of N1 and N2. And the variance of this thing is going to be sum over WI, where WI is the weight of each individual estimator. It's going to be WI squared times the variance of NI. Now you can show, I mean, I think it's pretty intuitive, that since these WIs are going to sum to 1, they're both less than 1, of course, this thing can always be lower than either one of the 2 in isolation, right? Assuming that you pick the W's correctly. Okay? And actually, you can pick the W's correctly. It's a very, very easy optimization problem. Standard Lagrangian multipliers solve it. Okay? So, easy to optimize the wastes. Okay, so are we cool so far? Okay? So, eventually, not surprisingly, this thing finishes, and now you've got these 2 intermediate relations. Okay? They're almost done, and so we then start up at the third level-wise step. And you now have this N3, so with this. Very good question. The answer is yes, and I'll talk about, there's a technical reason why that is. Yeah, so this is kind of a high-level overview. You'll see in about 2 minutes some of the details of this. Okay? So as this thing proceeds, the variance of N3 goes to 0. And the reason for that is that actually N3 is operating over tuples that are coming out of the top of the query plan. So after N3 completes, you've actually seen the entire output relation. And since all of the SQL aggregate functions can be computed in a single pass, right, or most of the nice user-defined ones, you're cool, and you can get a 0 variance estimate. So N3 goes to 0 when you're done with this thing. Okay? Okay. So now some details. So there are several key system design changes here, right? So you can't just plug this in to a standard database engine. What's different? Well, one thing is that the relational operators must communicate. So they're always searching for lucky result tuples. They're always chattering back and forth. And so you can't hide internal state, which is really the classic DBMS design, right? It's nice to think of these things as being independent. It makes for a nice, very nice kind of design interface, but in DBO, that's not possible. They got to talk. So to facilitate this communication, the relational operators actually participate in what I call a carefully choreographed dance. So they actually kind of proceed in lockstep with one another, as I'll talk about in a second. And another key thing is that you always need a semi-randomized order or output order from the relational operations. So all of this is based upon randomness. And so you got a big time problem if the tuples coming out of the first level-wise step are, say, sorted on the join key, right? Because then if you start plugging them into another estimate from a subsequent level, who knows what the correlation between the join key and the aggregate function might be. And so you got big time problems, okay? So DBO really is designed to take into account these things, okay? And of course, you need lots of nasty statistical analysis to characterize these randomized processes and actually get the variance. And if you're really interested in that, you can look at the paper for details. And unfortunately, in our paper, this takes up like 2 pages, which is bad because it makes it totally incomprehensible. Okay, so details on these level-wise steps. Okay, so a level-wise step has 2 phases, a scan phase and a merge phase. And the scan phase of a level-wise step is analogous to the sort phase of a sort-merge join, except, well, there's one scan phase for all the joins in a level-wise step. There is a round-robin processing of runs. So as you'll see, the scan phase, like I said, there's this kind of dance that these guys are doing. And that's really kind of fundamental to the scan phase. And another thing is that kind of a key difference is that in a standard sort-merge join, you typically use some kind of, say, lexicographic ordering. The ordering that you'll use is not important. But like I said, things have to come out of level-wise steps in a randomized order. So all sorting is actually not done based upon lexicographic ordering of the join key. Instead, it's done based upon a randomized ordering of the join key that's provided by a hash function, okay, which we'll call h. So here's actually an example of a scan phase, okay? And so what I've got here is I've got a 4-way join, and this level-wise step is composed of 2 two-way joins. And so we've got 2 attributes, 3 attributes, 2, and 2. And then I've had an extra column here, which, depending upon how you design this thing, may or may not actually be materialized, but it shows what the hash of B in this case is. B is the join key for this relation, because if you look, you're actually joining B and C here. And then we're joining G and H here. And so what I've depicted is the hashed value of the join key here, the hashed value of the join key here, and so on. Okay? Now, what you'll notice is that I've actually written this as a function. Okay, so we've got H1, H1, H2, and H2. And there was a question before about the these things being independent of one another. Okay? And so this hash function is actually parameterized on 2 things. One is, of course, it takes as an input the thing that it's hashing. But then we actually also take a key, okay, or a seed. And by using different seeds, it actually allows you to have independent sort orders. And so what happens is that all of the orderings of things coming out of these guys are all independent of one another. And so it facilitates the fact you don't have to worry about covariance between subsequent levels. Okay? And covariance is bad. Not necessarily from an accuracy point of view, but from an analysis point of view, it can be really nasty to deal with, which is why you have this parameter here. Okay, so what happens in this scan phase? Okay, so you start out by reading one run from each relation of the level-wise step into memory. Okay, so our assumption here is that you can hold 1/2 of each input relation in. Okay, now this, of course, would be a stupid thing because you probably wouldn't use this query plan here if you could have that much memory, but let's just, for simplicity, we'll assume that you're holding 1/2 of each input relation in memory. Okay, so after you load these things in from disk, the next thing that you do is all of these guys chatter back and forth, and they essentially look for output tuples. Okay, so any output tuples are immediately discovered, and these are used to produce this ni. Okay, in this case, if this were the first level step, n1. And so we find that we happen to be lucky enough to find one output tuple, because actually I think I've lost my join predicate, but there's a match here and here, and there's a match here and here, and a match here and here. Okay, so we got lucky and we got one. Okay? So, next thing that you do is you basically you kind of go for one step of sort merge join over here. So we're going to go ahead and sort everything that was in memory here, this run, on sorted order of the hashed value of the join key, and then it gets written back to disk. So we sort on H1 of B, and then write the result back to disk. Okay? So next thing is that you fill up your memory again. Okay? So these next block of tuples from R1 is now read into memory. Okay? You can probably guess what's going to happen next. You look, so these guys all chatter back and forth. You look for any result tuples you happen to discover, and we happen to discover one here. And these are used to guess, to update your estimate for the final answer to the query. And it should be clear that, again, since these estimators are all consistent, as you get more and more data, your variance goes down. Okay, so every time you read in another run, the user is seeing shrinking bounds. They're getting narrower and narrower. Okay? So, probably not surprising, the next step now is that this particular run is sorted on ascending order of the hashed join key and written back to disk. Now, what do? Well, roll in the next run into memory. Okay, oops. I think we're going to look over here. We try and find any matching tuples. And I think, since my next slide I go straight to the next step, I think we didn't happen to find any in this case. So we find no result tuples. We write that thing back to disk, sorted order of the hash function, load it in, keep on going, find some more result tuples. The process is repeated. Okay? And eventually, what happens is that when you're all done, you're essentially done with a sort phase of a couple of sort merge joins, but with the benefit that you've had all of these guarantees being given to the user as to what the final query result will be the whole way. Okay? So does this all make sense? I mean, it should also be clear, right, that if you had more runs here, you could just keep on repeating the process, right? There's nothing special about 2 runs. You just keep on going. Actually, also turns out that in practice, there's no reason that these things have to be broken up in even number of ways. Okay? You can have this relation broken up 2 ways, this relation broken up 10 ways, and then all that happens is that your kind of traversal pattern through the thing changes. Yeah?
What happens if you have duplicates? The example is all key joins.
Okay, so duplicates actually don't cause a problem. Okay? Actually, it's, well, I should back off from that. I'm actually going to, I'm going to consider duplicates in a second. There will be an important thing with respect to duplicates coming up.
They'll all appear clustered in the hash order. It doesn't matter how you hashed.
Yeah, okay, you're absolutely right. So this is actually a key thing, okay? And I'm going to talk about that particular point in depth. So that's actually a very good observation, okay? So it actually turns out that there are going to be different kinds of randomness that we're going to use at different levels. And the observation here is that at the first level, when you're doing this thing the first time around, assuming that everything is just randomly scrambled on disk, there's absolutely no correlation among the tuples, right? You could, a join key and a join key, you know, they're going to be in 2 different places. But coming out of the first level-wise step, what you're saying is they essentially come out in clumps based upon the join key, okay? And it actually turns out that this is true, but as long as when you're computing the variance and so on, you take this into account, you're cool, okay?
That can screw up the variance big time, right? If you have large chunks.
It actually doesn't cause a problem. So from a statistical point of view, so actually I can give you a prelude of so what do you do to handle this, okay? Well, it's actually very simple. You kind of take this big tuple, or this, let's say that you have 4 tuples that are coming out with the same join key, okay? Conceptually, what you do is you treat them as the same tuple, okay? So you kind of collapse them down to one tuple, and you treat them as a single tuple, and then kind of the problem goes away because there's no correlation because it's one thing, okay? Now what that means is that all of the properties of all those single tuples have to kind of be collapsed on top of each other when you're doing variance estimation and so on. But it actually turns out to not be a big deal. I mean, you can look at the paper for the details on that. So it's something that you're totally correct. You have to be very careful to take it into account. It has the effect of increasing variance. So it can, so actually when we implemented this the first thing around, we didn't do it correctly. And you could actually see that the confidence bounds are not accurate. So it does cause problems if you don't do it the right way. But it's something you can deal with. Okay? Okay, so some of the key points just to recap. So in this example, we had a bunch of updates to NI. Every time that you get a new run processed, you get an update to NI, and the confidence bounds the user sees shrink. So this NI is unbiased, assuming a random input order. So you can characterize the variance. It's pretty challenging. So now we're ready for the merge phase of this. Okay, so the merge phase in detail. So it's really just something like the merge phase of a couple of concurrent sort merge joins. So we got these things sorted into runs, so what do? Well, you load the head of each run from every input relation into memory, just like you would in a sort merge join. Store them in an appropriate in-memory data structure like a priority queue. And then you're going to go through, and actually the way this is implemented is we'll have multiple threads kind of doing this. So there'll be one thread associated with one of the joins, another thread associated with the other join. And so what happens is for all this stuff that's in memory, you kind of look just like in a classic sort merge join and ask, do I happen to have any result tuples? And you find that you got some that match up. Okay? And so they're then sent out on the output stream. And the key thing is that they're going to be sent out in the output stream in random order because the sort order is random, except that there will be some correlation in kind of these clumps, but we can take care of that. Okay? So at the same time, the second thread is doing the same thing over here, and you happen to find a bunch of output tuples. And actually, here's one of those clumps, right, where there's all the same join key. And so you keep on doing this. Okay? So I won't go through all the details, right? This is just standard sort merge join. A run gets exhausted, you read them in from disk, you look for matches, all this stuff. Okay? And so eventually, you're totally done. And all of these tuples have been discovered. You've got all of the results from R1 join R2 and R3 join R4, and they're sent on the output stream. And the way that this works in practice, the way it's actually implemented, is that the two level-wise steps actually, like, take the bottom level-wise step and the next one. They're actually operating concurrently, and as soon as you discover an output tuple from the bottom one, it gets pipelined directly into the next one. So what this means is that at every instant, there's always some scan phase operating, right? So they don't actually operate, write their stuff back to disk, and so on. You've always got a scan phase operating, and this is key because it means that you're always updating the estimates. Okay, so a few more details. Okay, so there's one thing here. Of course, all of this is predicated upon the fact that you are dealing with bushy query plans. Okay? Now, let's say that you have a query plan that either A, is not bushy. Well, put it this way. Let's say you have a query that has no bushy query plan, or where, as an alternative, maybe the bushy query plan is just a really bad option. Okay? So it turns out that you can deal with it. So here's an example, right, where you've got essentially what is a very common star join in a data warehouse, where you've got a central fact table and you're essentially adding the dimension tables to it. So this doesn't lend itself to a bushy query plan. Actually, it's kind of impossible. You're going to have a left deep or a right deep plan, right? So what do? Well, there's actually a really simple trick. So we add these kind of dummy operators into the query plan, which are, they don't do anything other than scan and reorder the input relation. Okay? So that we essentially play a trick. So you create a level-wise step out of this thing. So the problem is that you can't just ignore T and U, right? So if you go back to this last thing right here, there's no way in which you could just have a level-wise step here and guess the answer to the query, because you need to see tuples from T and U to know what's going on, right? So what we do is we do a scan, so you have a level-wise step here, but these operations actually don't do any joins or anything, okay? All they do is they just write back the data to disk in a different order. Now you can argue that this is wasted effort, but hopefully, well, first of all, your query optimization should take this into account and try and avoid this. And in cases where it can't be avoided, like in a star schema, you would assume that hopefully these relations are relatively small compared to, say, R in this case, which is forming the backbone of the query plan. And so really all of your time and effort is concentrated with this thing. And so a scan of reorder hopefully isn't going to be too nasty. Okay, so computing accuracy guarantees. So this is not easy. So there are a couple of different kinds of randomization. The problem is that actually at the bottom level, you've got this, you're kind of randomly ordering data. When stuff comes out of these joins, it's actually coming out according to a Bernoulli sampling. And the reason there is that you actually, well, I probably won't go into that, but let's just say there are two kinds of randomization. Okay, there are chunks of tuples that you have to take care of. And there's lots of algebra and recursive variance formulas, covariance to deal with, but it can be done. Okay, so how well does all this work? We'll have one just kind of quick performance result, and that is here's an example. So our prototype, so we take this TPCH query here, and ran it in DBO, and then also in Postgres. Okay, so DBO actually turns out to be significantly faster than Postgres. Now it's been pointed out to me, this is to run to completion. So it's been pointed out to me, but so Postgres is probably the worst option you could ever choose for an analytic query like this. That probably, if you want to use a free database, that MySQL is a much better choice, and of course the commercial ones are going to do better still. But the point here is not to say that we've got the fastest query processing engine ever. It's that you can do all the statistical stuff and it doesn't kill you. Okay? We're at least competitive with a decent DBMS. And so this plot here, what this shows is it shows a plot of the bound width. This is the ratio of the confidence bound width divided by the current estimate as a function of time. So this is kind of an error on the query. And so what you see is you start out, you've got an error of 1. Which what this means is that when you start out, you're essentially doing a ripple join. And we're going to run out of memory after a few seconds. So the point here is that the ripple join is essentially useless. It doesn't get you anywhere. But soon after the ripple join ends, DBO kicks in doing all its stuff, and the confidence bounds continue to drop very nicely. And you see that, so these black lines indicate where there's a switch over to a new level-wise step. And you see that you kind of get this precipitous, and this is actually on an exponential or logarithmic scale. You kind of get this exponential drop in the width of the confidence bounds. And that's because, like I said, you're compacting the relations, right, as they go through. So you have a lot less variation. Yeah?
Here your line item table is one of the things being reordered. Does that add a lot of overhead?
Yeah. So in this case, though, so actually, I can't remember exactly what query this is, but there is a selection predicate here. So that might have actually dealt with that.
Related question. So instead of comparing with Postgres, how much time did it take to run the same query without the reorder operators?
Oh, without the reorder operator. I mean, we have that. I don't know off the top of my head. So, the key point there, right, is that if you do the reorder in a bad way, you're going to really hurt yourself. Okay, so there's no disputing that fact, right? If you have to reorder a huge relation, then you're going to get killed, right? So the optimizer has to know about this, of course, and take this into account. Yes, I mean, your point's well taken. Yeah. Okay. So the rest of the talk after this now, looks like I have about 15 minutes left, is on extensions to this. So are there any questions on the material so far? Yeah.
Do you use index?
No. Okay, so this is another thing is that, yeah, so our prototype, actually we're adding indexing in, but this stuff doesn't use indexing. Okay? And indexing actually changes the whole thing around again. Because one place where we get hurt is that a primary index, like a clustering index, is bad. This causes us problems because that kills randomness. Okay, now there are research issues there, but you can't just take a clustering index and use it in DBO. Now we can use a secondary index just like anyone else can. Okay, the secondary index is not a problem, because there's actually good work on sampling from secondary indexes we can use directly. But for cases where something like a clustering index is going to really help out, we're going to get killed.
And also, do you support non-equality join?
Yes, so non-equality join. But that's actually an interesting one because we support that no problem. Okay, so you're going to use like a nested loops, of course. But it actually turns out that that's kind of, you don't need all of our stuff when you use nested loops. So you can actually use something that's very similar to a classic ripple join. You can do a nested loops ripple join and it doesn't really hurt. So put it this way, we can handle non-equality stuff. It's almost the uninteresting case for us. Okay? Yeah.
How will you deal with the slew of the transformation rules that exist in query optimization?
Yeah, so actually one of my last slides will say that, so what we haven't, since we're actually talking about just throwing out most of what's there, okay? I mean, on the one hand, especially at a place like say the SQL Server group, they'll see this and go, okay, whatever. Because we don't, you really have to start from scratch, right? That being said, so optimization, I think, it's hard. I mean, I'll just say you're.
No, I mean, I guess I'm saying that I'm not talking about how you build an algorithm.
Okay.
Itself is an interesting question. But let's say I want to use the swap between or pushing the group by down.
Okay.
In your query tree. So the group bys are not pushed right on the top.
Mm-hmm.
Group by is followed by job. How well you can deal with these operators being interspersed?
Oh, actually, great question. So it turns out that to be useful, we actually have to push the group by all the way down. Okay? You have to, and the reason is that if you don't, I mean, you're doing estimates over groups,
right.
And if you don't know that you're part of a group, because you haven't pushed it down far enough, you're going to be in trouble. So we actually have to push it down, or else we can't.
But it also limits then the class of aggregates you can have.
Yes.
Which is a limitation in an analytical world.
Sure. Yeah, I mean, I have to admit, I haven't thought really deeply about exactly how that hurts things, but you're right. Yeah.
I was wondering, so it looks like you need to kind of, at a certain level, you need to read all these relations at the same kind of relative speed or so, right? Like if you've read 50% from one, you want to read about 50% from the other so that you kind of see like the best possible bounds, right? Error bounds.
Well, so
or can you read them at totally different speeds?
you can read them at different speeds. And actually, this is something we're working on now. Different speeds is going to give you better. So it turns out that there's an optimization problem here. And intuitively, the result is that what you do is you actually throw more memory and more reads at relations that are smaller, okay, to a certain extent. And the reason for that is that, let's say that you put an extra few megs towards a huge relation, which percentage-wise gets you a very little amount of it. But you put a few megs towards a small relation, which allows you to read most of it. The error you incur due to the sampling is much smaller. I mean, the extra error you get rid of by putting those extra megs towards the small relation is much larger. You kill more error. Okay, so there's all kinds of stuff there. You're right.
Then at the next level, you would have a harder problem because it's pipelined, and then you would have to estimate somehow these sizes.
Yeah. Well, okay. So what would still happen is that you would still have this kind of dance where it wouldn't really change, I think, anything in the next level. Okay. So you might be hitting things at different rates, or hitting one harder originally, which is going to tend to make the thing dip down faster. But in the end, stuff is still going to work the same way subsequently. Now, I guess one problem would be if you go through one of the relations much faster and it causes someone above you to kind of block what they're doing. Yeah, so there's.
I guess to.
It is. I mean, actually, this is, like I said, this is something we're looking at now. It's certainly non-trivial.
Somewhat related to the earlier questions, like what class of things can you handle using this technique?
What class of?
What class of queries can you handle in this?
Okay, yeah, so
handle exception or minus?
Yeah, actually, so I'm running out of time. I have actually another half of a talk, so I'll try and go over that in 5 minutes probably, or if I have any time.
If you want, you can go a little bit.
Okay. Anyway, subtraction actually is so hold that. I'll at least start on that. Okay.
That question only answered the aggregation part, right? But and the other part is clearly for TCPH queries, there are some subqueries, and I don't know whether you handle that.
Yeah, so that's actually the same question, because if you look at the TPCH, I mean, actually, this is exactly my next few slides. So. Yeah.
I had one more question.
Okay.
So, when you execute, right, you start off with error being 1 or relative error being 1 and it becomes 0 at the end.
Mm-hmm.
But it's very hard to say how this moves from 1 to 0. And I can construct cases where it remains 1 almost to the end and becomes 0. So,
Well, actually,
in practice it may not happen for many queries, but it's possible to construct artificial data sets where it becomes 1 to 0.
okay, so you have to be a little bit careful there. So one thing is that in this case, the 1 was an accident. Okay, it can actually start out kind of anywhere. It can actually start out at 1,000. You could actually have, I mean, there's no reason that you couldn't have an estimate where the confidence, like an estimate of 10, and the confidence interval goes from negative huge to positive big. Okay, Now, if you're saying that there could be a case where everything stays really bad for a long time, okay, I can buy that. So one thing that comes to mind, okay, so one thing we know about is if you have a group by with a lot of groups, okay, so the problem there is that your selective queries aren't necessarily a problem for us because we just throw out in the first scan everything we don't need. But when you have a group by query with 1,000 groups, okay, or more, then this is essentially a selective query on a per group basis for which you can't throw out anything because you still need all the data for the other groups. Okay, so this is a case where that you could construct that could possibly have big problems for us. Okay, so yeah, I mean, so it's really a matter of yeah, I mean, it's sure.
That's not the case even with joins, right? You have duplicates, a lot of duplicates on one side. So basically you have a foreign key join where you have a key and the foreign key is got like, that's almost the entire table. So it's important for you to have an accurate estimation. It's important to the key be joined with all of these. And the key may appear really low down in your sort order because it's a random order. In fact, it will appear low down.
Actually, I don't agree with that one. Okay. So actually, I mean, you can characterize this process statistically, okay? So it actually doesn't matter about things like keys. When it comes down to it, okay, variance is incurred so think of, let's say that you just do a nested loops join, okay? And every pair of tuples that you look at, you take that value, the value of the aggregate applied to the pair of tuples. You give it a 0 if the where clause doesn't match. And you give it the aggregate value squared if it does match. So let's say you take that and you look at that sum. Okay? If that sum is large, then for statistical reasons you're going to have large variance. That's the major component in the variance formula. Okay? It doesn't say anything about keys. So things that kill you, the ways that you're going to get that thing to be large, relatively speaking, so if it's large relative to the final answer, the way that happens is if you got a lot of zeros in there and a lot of big values that end up being squared in this whole formula. So those are the kind of things that hurt you. Having multiple like duplicates actually doesn't inherently hurt.
So remind me, what is your semantics or how you quantify the errors when you have a group by queries? What's the model of error you're taking? I know that you can define it in multiple ways.
Okay. Yeah, so that's actually we've got, so one thing, we've actually got a 50-page paper submitted on that question. But the simple, actually, yeah, so the very simple answer to that is that you could imagine you just take every group, you give the estimate, and then you tell, I'm going to say with 99% probability, the real answer for this group is within here.
Well, but are you going to allow for missing of some groups? That's kind of crucial, right? Because there will be some extremely small groups.
So this is where it gets interesting, right? You can miss groups. From a statistical point of view, a very interesting, almost purely statistical problem is that there's actually correlations induced among groups. So statistically speaking, a user has to look at one group, determine what they think based upon that, make a decision, and then erase that from their mind when they look at the second one. Okay, which probably isn't feasible. I mean, this is why, yeah. Okay. So this is a... Okay. So what I'll try to do, since I've only got just a couple of minutes left, and I hate to keep people here, is just give a very brief overview of some of the other stuff. Okay? So like a couple people brought up, right? Project, select, join queries are great, but subqueries happen in analytic processing. Okay? So really, if you look at the Pch benchmark, okay, there are really two classes of queries with subqueries. So, I mean, some of the subqueries they're just syntactic sugar. You can rewrite the thing so it doesn't have any. But the real ones where there's real correlated subqueries, you can't just rewrite. Okay, there's two kinds. One is the set-based. Okay, so the key ones, so essentially subtraction and intersection are the interesting ones. So here's an example, right? So we ask a query, we're saying, how much money are we paying to salespeople who, among other things, which are the dots, have not made a sale? Okay, so that would be an example of something we want to deal with. Okay, so that's one class of queries that's interesting. So the other thing that you commonly see in analytic processing are correlated aggregates. Okay, so there are probably 2 or 3 set-based queries in the TPCH and 2 or 3 correlated aggregates in the TPCH, and everything else is select, project, join. Okay, so So here's an example, right? So you want which departments have a relatively high revenue per item, okay? So you got inside, you've got this query that gets you the average revenue, and you want those that have 1.5 times higher than the average, okay? And this is very challenging to incorporate into DBO, okay? And this is something actually that we're working on a lot right now, okay? And so let's see. Well, what I'll do is just in the couple minutes I have left here is I'll just talk about why this is hard, and then leave any kind of talk about the solutions to future when we write a paper on this. Okay, so why the set-based operations are hard. Well, so example, let's say that you have a sum or some kind of aggregate function over effectively Q1, which is a relational algebra expression, minus Q2, which is another expression. Okay? So we'll focus on just subtraction for simplicity. So the reason this is hard is that this thing is effectively like having a relational selection predicate over tuples in Q1, where that predicate depends upon the property of Q2. What I mean by that is that when you've got just a select project join query, when you see a tuple, where you're trying to figure out that this tuple is accepted by the relational selection predicate in the where clause, you just apply the where clause and you're done. Okay? In this case, you've essentially, one way to think is you got a where clause that depends upon another query, right? And that's why it's hard, okay? So if you're doing sampling, and all you have is a sample out of Q2, you got this Q2 prime, then how do you evaluate this kind of imaginary where clause, right? How do you know that simply because T, which you found to be in Q1, doesn't have a match in Q2 prime, how do you know that it's never going to have a match in Q2? Okay? Well, you don't. So then the result of this is that really all pure and practical sampling-based solutions have bias. Okay? So actually, it turns out, just as an aside, we wrote almost a purely mathematical paper on this problem in the end. We came up actually with an unbiased solution for this. Okay? But it's actually effectively a random number generator. Okay? Because the variance, the variance bias trade-off in this case is so bad that pure sampling-based method, it's impossible. Now, a statistician would say, okay, trade some of that bias or some of that variance for a little bit of bias. But the problem we have here is that all of these things actually depend upon knowing something about Q2. So to set the variance bias trade-off, you got to know more than you could possibly know. Okay? So the result is that all these things are really bad. Okay, they're really hard. And so what's our solution? Well, in 30 seconds, our solution to this, the thing we're working on. So what you got to do is you've effectively got to, when you're going through and doing these level-wise steps, the key thing that you do is that you got a Q1 level-wise step and a Q2 level-wise step. So you split it in half. Okay? As your Q1 level-wise step is going through, it's discovering output tuples. You let your Q2 level-wise step kind of lag behind a little bit. And then these tuples that it discovers, that Q1 discovers, get plugged into the Q2, which then actually searches through all of the output relations. Okay, so it gets rid of most of the randomness. And it discovers exact statistics about these Q1 tuples. Okay? So what you effectively do is, by really carefully designing how stuff works, you can get rid of this problem that you're guessing whether or not tuples appear.
But at the end, you have to still get back to a randomized thing for the next step out, right?
Yes, you do. Yeah. And actually, what I gave is, that's. So I could probably spend another hour talking about that, but we'll. Okay, so any other questions or comments or anything?
For some operations, it's known that you can't have a solution based on sampling, right? Or count the number of distinct values.
Great question. Okay, I disagree. Okay, so you have to be careful. Actually, it turns out that subtraction is actually.
I'll appeal to the author here, but.
well, you have to be you have to be careful. Okay, what you say. So it turns out that so Q1 minus Q2, this thing right here is actually strictly a generalization of the count distinct. Okay. So the stuff like surrogates done and all that, this is strictly a generalization of that, okay? So now, I mean, like so what's been shown, right? Of course, so there's really interesting work. People have worked on that problem for a lot of time, okay? And actually, it turns out that, like I mentioned, we actually have an unbiased estimator for this thing. So it turns out that there's a very famous unbiased estimator for the count distinct problem, and actually ours is strictly a generalization of that, okay? So you have to, so for a purely sampling-based solution, okay, I agree with you that it's bad. I mean, you end up having random number generators, okay? But here's the key thing, right? And DBO, it's not a pure sampling-based solution, right? Because you're actually going through these levels and so on. And so the key thing that we have that when you're doing pure sampling you don't have is that we can cheat, right? We can do things like as level-wise step here is going through, it can take counts and statistics and look for stuff.
So what will happen if, so let's say I just have one column, nothing else in my data. That's all. I wanted to count this thing.
Okay.
So what exactly will DBO do?
Well, okay, so in that case, so the way that you rewrite this query as a count distinct is you actually have, for one column or one table, you would actually do, so in SQL, the query is something like select count. So you attach an arbitrary ID with every tuple in the relation, okay? Then you say select count, and then star, and then you'd say from my relation where there doesn't exist another tuple in the other relation that has an ID.
But now you are increasing the processing cost. You turned it into effectively a join, not join, but whatever. There are two iterators effectively.
Yes.
So as against the basic, so there's a trade-off between the processing, as was pointed out, is changed. So it's a different ballgame.
Oh yes. So you have to. So I agree with you. Okay. So you actually wouldn't want to. So I'll be careful here. Okay. So I'm not saying that you would want to answer a count distinct this way.
But you're saying that you can get an estimation if you have to use
right.
this style of processing.
Yeah, and actually it turns out, I mean, from the theoretical point of view, okay, like I said, so we actually, when we were first started worrying about this, we came up with an extremely elaborate, provably unbiased estimator, okay? Since it only looks at samples, I mean, it's just a very simple computation. And you could actually rewrite the query in this fashion and then use our estimator, and it's going to be exactly equivalent to, I guess, like, what is it, the Schlosser estimator or the, yeah. And so you...
Well, that's interesting. I mean, I think what you're saying is that, well, if you change the processing, and of course, there is an entire thing in terms of the, to get to a certain level of accuracy of estimation, how much time you're spending. Because after all, you're doing that to save time, right? I mean, to some extent. But it's an interesting observation, definitely.
Yeah, I mean, I think, the key thing overall here is that the motivation for sampling for count distinct is query optimization. Right? Gathering statistics. Here we have a totally different thing. Our motivation is answering aggregate queries. So we can exploit things like indexing, we can exploit internal state. We have a whole, our world of what we can look at is much greater than just the sample. So that's why we can do better.
Any other questions? We have peppered you with a lot of questions for that talk.
No, it's great.
Any other questions? Thank you very much.
Okay, well, thanks for having me.